Hello and welcome. Today we're diving into a critical component of modern computing that makes your devices fast: advanced branch prediction and processors. Modern processors execute instructions at an incredible speed, often using techniques like pipelining, where multiple instructions are processed simultaneously in stages. However, conditional branch instructions, like if-else statements in code, present a challenge. The processor doesn't know which path of execution to take until the condition is actually evaluated. A wrong guess, called a misprediction, means the processor has to discard the work done on the wrong path, flush its pipeline, and fetch instructions from the correct path. This wastes valuable clock cycles and significantly degrades performance. Effective branch prediction is absolutely crucial to minimize these penalties. While basic branch predictors have existed for decades, today's demand for ever-increasing performance has pushed the development of highly sophisticated techniques. Simple predictors, such as always predicting a branch will be taken, or using a basic 2-bit counter for each branch, just don't cut it anymore. Modern programs have complex control flows, and branch behavior can depend on a long history of previous branches or data values. To achieve the high prediction accuracies, often well over 95% required by today's processors, we need more advanced mechanisms. Let's explore some key advanced branch prediction techniques. One of the early advancements was 2-level adaptive predictors. These use a first level, the branch history register, to record the outcomes of recent branches. This history pattern then indexes into a second level, the pattern history table, which contains a predictor for that specific history. It's like learning from past sequences of branch outcomes. Next, we have hybrid or tournament predictors. These systems recognize that no single prediction strategy is optimal for all types of branches, so they employ multiple different prediction schemes simultaneously. A meta-predictor then intelligently chooses which predictor's output to use for the current branch, often learning which base predictor is more accurate for a given situation. Inspired by machine learning, neural predictors, particularly perceptron predictors, represent another significant leap. They use a simple form of a neural network. Features derived from the branch history are given weights, and a weighted sum determines the prediction, taken or not taken. These weights are trained based on actual branch outcomes, allowing the predictor to learn complex correlations. The TAGE, or Tagged Geometric History Length Predictor, is a state-of-the-art example that incorporates similar ideas. TAGE uses multiple tables, each indexed by different lengths of branch history, giving more weight to longer, specific matching histories. It's highly effective at capturing very long history patterns while managing hardware costs. Other specialized predictors also play a role. Loop predictors are designed to accurately predict the behavior of loops, which are very common. Indirect branch predictors tackle the challenge of branches where the target address itself can change dynamically, like in virtual function calls. And the return address stack is vital for predicting the target of function return instructions. The impact of these advanced branch prediction techniques is profound. They enable deeper pipelines and wider instruction issue widths in processors, which are fundamental for increasing the number of instructions per cycle, or IPC. Without highly accurate predictors, the performance gains from these microarchitectural features would be severely limited by frequent pipeline flushes. Despite these successes, research continues. Current challenges include reducing the power consumption of these sophisticated predictors, capturing even longer-range historical dependencies without prohibitive hardware costs, and more effectively incorporating data value history into predictions. The application of newer machine learning models also holds promise for future advancements. In conclusion, advanced branch prediction is a cornerstone of modern high-performance CPU design. Techniques like TAGE and neural predictors are essential for keeping the execution units fed with a correct stream of instructions, enabling the remarkable performance we see in today's processors. The quest for even better prediction accuracy and efficiency continues to drive innovation in CPU architecture. Thanks for listening.